And welcome back. Now this week we're going to be talking first of all about this little device here, which is in fact a rotary encoder. So yeah, we'll talk about this. Here's another one here. Look, just so you can see what it is, a rotary encoder. Okay, so it's got 5 pins, but frankly it's less complicated than that. There's 2 for power, so that leaves 3, and one of them, the marked SSW, that's a little switch. So you can push this, and that's a switch, just basically on off. So we've actually got 2 pins, the top where it says clock and DT for data, more commonly known as pin A and pin B, to be quite frank. And that's it. And it tells you basically which way round you're turning this device. So if we quickly put a knob on here so I can show you. If making a PCB is a bit of a puzzle to you, let JLCPCB help you put all the pieces in the right place. Easy EDA is an intuitive electronic design tool, just as I'm showing you here. And when you've done that, you can convert it into a PCB like this one here. And you can view it in 3D and see exactly how it's going to look before you order it. It's easy to order from JLCPCB directly from within Easy EDA, with fast, reliable deliveries, and now $2 for 5 pieces, including aluminium boards. They can even assemble them for you at no extra charge. Why don't you see what JLCPCB can offer you today? This rotary encoder just goes round and round and round and round. There's no stop like a standard potentiometer. You know, a standard potentiometer would probably end there, that sort of position, and start about there. But this one just keeps going and going and going and going. Now, they're used a lot in cars for tuning devices and indeed volume controls these days. My one certainly does. And they're easy to use, easy to program, as I'll show you. And in fact, if you look at that previous video, you'll see how easy it is anyway. But this is an alternative way of doing it and doesn't have to look at switch bounce as such. It caters for it, but it doesn't actually do what I do in that original sketch. Firstly, though, there's some very sad news. Yeah, I know. My multimeter that I've only had for 2 years, and I was quite pleased with it when I've been using it, has gone foobar. Yeah, that's fouled up beyond all recognition. Sort of. Well, it was, and I sort of half fixed it now. But I'll show you what it sort of does, or perhaps what it doesn't do would be easier, wouldn't it? So this is it in the auto range, which is what I keep it on an awful lot. There's an auto range for resistance, and there's one for diodes and capacitors. All sorts of things like that, and it's been pretty good and very accurate. And one of the good things is I can go right down to sub microamp detection to measure things like current consumptions for bare naked Arduino chips. Yeah, that's a bit annoying actually. The backlight goes off after about 15 seconds. The newer models tend not to. But anyway, let me switch that back on and I'll show you what happens. I'm on auto mode at the moment for resistance. It says mega ohms because it can't detect anything. Now I've got here a resistor and it's 100 ohms, as you can probably see, 100 ohms. So if I put that across the probes, what do we get? We get, I don't know what that is. Yes, and that's the problem. So what happened was I came in one day and it said calibration error. Well, a little bit more terse than that, but anyway, it was a calibration error. So of course, onto the internet I went, and it says, oh, you've got to recalibrate it, and there are no manuals to tell you how to do that. You just have to wing it. But of course, other people have been there before me, and they said, right, do this, press this button, press the other one, and yeah, it said. The problem is really you need multiples of 3 of everything. So you need like a 30 ohm, a 300 ohm, a 3K, 30K, 300K, 3 meg, 30 meg, a bit like that. And again with nanofarads and microfarads and all the rest of it. And they're not standard values. So I was scrabbling around trying to concoct values like that. And I've got it working sort of now. But frankly, I'm thinking, do you know what? I don't trust it anymore. Because I've now calibrated it with components that are here that are, well, some might be accurate, some might not be, but I think, yeah, I bought this to be, accurate, didn't I, really? And this cost me, I think, about $100 2 years ago. And it's been fine up to now, but the fact it didn't have this calibration error on here after 2 years, and to send it back to a proper company that does calibration costs about 30 UK pounds, which is about what? $45, can't work it out. My brain cell, my second brain cell is overloaded today. Anyway, the point is, I've had a look on the internet and you can get some very, very good multimeters for far less than what I paid for this 2 years ago. And I'm thinking, do you know what? If the lifespan of a multimeter is only, 24 months, then maybe you should go down in price and get something that will work for a couple of years quite happily. And when it does go foobar, buy something else that's reasonably cheap. So I had a look on the internet and this is what I came up with. Yes, of course, the industry standard, I could buy a Fluke for £209. What's that? $250, $60? I don't know. Ridiculous amount of money. No, I'm not spending anywhere near that. You must be joking. This is the sort of meter you get if you're an electronics engineer working for a company and they've standardized on Flukes or something because they need to. Their business depends on the multimeters working properly. But no, I'm not buying that, even if that is a good price. The next one I found was this one, a UNI-T one. Now, I've got a desktop UNI-T multimeter. It's over there, though, on my other workbench where I sort of build stuff and test stuff. And I've been using that ever since. And it's great. A little bit noisy. It switches on and off again by itself and beeps, which has meant I disabled the beeper, but now I need the beeper back on again because I haven't got the continuity beeper working. I know. Now this is one of the higher end UNI-T ones, $89. No, I'm not going to spend that. There was a different model. This one's a 61E. You notice up here, 22,000 count. I don't need anything like that. I'm not an electronics engineer working for a company, am I? A 6,000 count would be fine, and they're about $50. But even then I'm thinking, oh no, $50 for what I do here, a little bit of measuring, I need it to have certain functionality, but I don't need the nth degree of, accuracy and decimal places and all that. So I thought, okay, what else have they got? Well, they've got this one here. This is fairly well thought of. Now this is a company that I hadn't previously thought of, is ANENG. AN9002, as you can see, it's $28, which is pretty good. You can buy that in the UK as well for 25 quid or something. And it seems to have most things that I need, if not all things that I need. I'm still investigating. And truth be told, I'm still thinking, do I actually need to buy another one? Or can I get by with my old multimeter plus the bench one and just think, leave it. Until you know that you need another one, don't buy one. Yeah, good thinking really, but well, anyway, there's this one. That picture on the right, by the way, this thing here, that's actually a phone because this is Bluetooth enabled and it sends the data from the multimeter to your phone as a sort of a mirror image, like you're casting to a screen from your phone. I'm not quite sure of the advantage of that, quite frankly, but okay, it seems to be something that the reviewers felt was valuable. Okay, but more to the point, this particular one, this ANENG, was okay in terms of functionality and everything else that it could do, diode testing and all that, and voltage, and it was pretty accurate. So I'm thinking, you know what, for $28, well, all right, nearly 29, 24 or £5, something like that, compared to my $100 foobar one, I'm thinking, well, perhaps this will do me. Your thoughts, comments and suggestions, don't say Fluke, I'm not getting one, I don't care how good value they are, would be gratefully received underneath, because I'm not going to rush into this. I'm going to see if I need one first. But your feedback, people who have bought stuff either locally or from China, do let me know, because I suspect in the fullness of time I will have to replace that one that's gone a bit funny. Yeah, the bell. Okay, right, back to the main subject matter of this video. Now, the reason why I'm looking at this again today is because the original code that I wrote had to cater for switch bounce in here, because basically inside here on some sort of camshaft or something, there are two, quite literally, switches like this, right? And so they're normally off, so the circuitry in here brings them high, so you don't need to use input pull up, you just use input, because the VCC in here is already connected to those switches via a 10k resistor at the back here, right? So normally the switches are not shorted to ground, they're just sort of left floating, but the 10k resistor brings it high. So your sketch can determine, as you turn that, as each one goes down and then the following one and that one comes up and that one comes up, it can determine that, and the sequence of this happening determines the rotation. Great, but in ultra slow motion what happens is this, of course, your switch goes down and then because of the mechanical inertia, bounces a couple of times, right? Sometimes it's hardly at all. Sometimes it can be really quite a lot in a very, very small time frame. You might be talking 1 millisecond, 2 milliseconds. In fact, when I was reading an article about switch bounce, the guy who had done a lot of work on this said he's only ever seen one switch that bounced for 20 milliseconds, right? So 5 is considered normal. So the original code said, right, as soon as I detect a change in the switch, so one switch goes low, it then, if there's bounce, so it's coming off low and then back again, your microcontroller will detect that. And it goes, oh, you've gone high and then back low again. So to prevent that, my code says, oh, hang on, you've interrupted me again, but you were here only a quarter of a millisecond ago. No, I'm not. I'm just ignoring that. Okay. In fact, for 5 milliseconds, I ignore any future, bouncing around of a switch. So as the switches go and bounce, there's 5 milliseconds delay as each one goes down and then back up. And that works pretty well. In fact, it works very well. But I had a viewer say, oi, Ralph. Well, actually, he wasn't that rude. He just said, I've got an alternative algorithm for rotary encoders that do not require any dead time. So, because remember, I'm stopping for 5 milliseconds waiting for this bounce that may or may not occur on each switch. So there's 5 milliseconds every time there's an interrupt on that rotary encoder. Say, right, you've interrupted me once and I'm not going to accept anything else now for 5 milliseconds. He says, I don't need to do that. What he does is says, when the switch goes down, the next logical position must be for this one to go down. Right? It can't, mechanically, it cannot work any other way. So if this one has gone down and then bounced about, it goes, that's the nonsense. You can't go up and down again on the same switch when you've already gone down once. So he says, I'll just ignore that. Even though you read it and accepted it because your microcontroller is very fast, it can deal with all those. He says, no, I'm ignoring that down again, that double down. And it can do it 3 or 4 times. It goes, no, that's rubbish. And eventually this one goes down. And it goes, that's valid. But when this one bounces about, it goes, no, that's invalid as well. And ditto when it goes high. So it's gone high. And it might bounce to low again, unlikely to go all the way down. But anyway, whatever it's doing, he says, I just ignore these impossible states. Let me show you the actual comment that he left. Yeah, I know, it's a long time ago. Right, so here's the comment, right? Now this is Marko Pinteric. And it says there, 4 months ago, let me just get this on my screen so I've got it out. So 4 months ago, well, it's September 2021 now. So this was 4 months ago. I can't work it out. Is it April or something like that? Anyway, I read it, but I was in the middle of a house move. I don't think my workshop was even built properly. So I took his article. He's written a whole article, and I'll show you that, and put it on my GitHub as well. A link to it anyway. And I tried to understand the code, and my third brain cell died through exhaustion. It just could not cope with it. But eventually, over time, I thought, I understand what you're doing now. Great. But what he doesn't do is use interrupts. Now, I wasn't happy with that. He was polling within the loop. And I saw no reason to do that. One, because you could be doing anything in that loop, yeah, and, long stuff. And you might miss a pulse. So you're doing long stuff in your loop going round. A pulse happens on one of these switches and you actually miss it. You don't want that. I think, well, why is he not using interrupts? Now, on the Arduino, you've only got 2 hardware interrupts, pins 2 and 3. Yeah, GPIO 2 and 3, that is. So you'd have to use both for pin A and pin B because you need all the states to be detected for the code to determine whether or not it's a possible combination or whether it's one of these impossible combinations. But on an ESP32, which is where I'm coming from now because I may introduce this into my smart heater controller to adjust the temperature, might. It's not a problem because any pin just about can be an interrupt. So if you're using an Arduino with this, yeah, you can use it, but then you can't use any more hardware interrupts. That might not be an issue, but just bear that in mind. So he says here, and I'm sure you've read this by now, he says, I've done it differently. So I took his code, massaged it, put it into an interrupt routine as well, and, well, we'll have a look at it in just a sec. In fact, let's look at it first and then we'll go through the code very briefly. I'm not going to go through this line by line. There's no need. Right, let's bring up the cool term window, which is this one here. Yep, that's it. Right. So the cool term window will tell me when I move this rotary encoder here backwards and forwards, and we'll see it all come up over there in that cool term. So I'm going to move it right one click. There we are. So it says right 0.5. Because I'm doing this in 0.5 steps, well, mathematically it's one complete click. Because in a temperature control, you probably want to go from 20 to 20.5 to 21, 21.5. Yeah. For all our American friends out there, we're talking centigrade. Obviously, I'm not sitting in a freezer here. So I don't know what 20 is, about 66, is it? Somewhere around there. Room temperature-ish. Yeah, I probably want it up to about 23 in here, 24. So as I turn right, so look, click, 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 it's going up in these half-degree increments. And when I turn it anti-clockwise, you can see it going back down again. Yeah. Now, one of the things Marko says, it will go negative if I carry on, by the way. Look. Now, one of the things Marko says, he says you can do it fast or slow. So I'm going to whiz round and do a few. Look, whiz, really fast, really backwards and forwards. Now, I'll let you pause the video and have a look if you don't believe me. If you look at some of the output on here, you'll see that there's no missteps. There's no going clockwise and then having the occasional, oh, you've gone anti-clockwise. It doesn't work like that. This just works. Yeah, to borrow Apple's phrase. I think it was Apple, wasn't it? And it just works, and I like it. So if we look at the code behind this window, you can see that I've defined the pin A and pin B. That's what it says. It says clock and DT on that rotary encoder, clock and data, but I don't know why they do that. Here's the variable that we're using to count up the rotations, left or right, just keeping track of it basically. Here's the volatile variable that's used within the interrupt routine. Now, an interrupt routine is exactly what it says. Your code could be doing anything, but once that hardware pin gets the value low, high, rising, falling, whatever it needs to get to trigger, it will trigger immediately and run the routine you've told it to run. Now we'll come on to that. Here's the interrupt routine then, right? So all it does is say there was movement. That's all. That's all that rotary encoder does. So it's fast. It's in and out within a fraction of a second, far less than a millisecond. So bang, there was movement. And that leaves the loop then to figure out, oh, there was movement in its, course of time as it runs around doing everything else. It goes, oh, there's movement. I better go and find out what that was then. And to find out what it was, it runs this little thing here, check rotary encoder. So let's have a look what that does. Now you can see all this code here, and I'm not going to go into this because it's just, we'd spend an hour talking about it. Well, it took me 4 months to understand it, all right? So what he's saying are all these things here are the possible valid combinations going from, rotary encoder as you're clicking round and the two pins are going high and low. These are all the valid combinations you can have, with the 14 being the invalid option. So we're reading the two pins because we've discovered that there was movement. The interrupt routine said there was movement. So we figure out what movement there was. And by jiggling around all the bits and all that, we return either the +1 or +1 going clockwise, -1 going anti-clockwise. And if it's not one of those, it's an impossible transition. So it goes, no, that was nothing. Ignore it. Fine. Good. Right. Now, I'll leave this code up on the GitHub so you can look at it in more detail. But believe me, if I was to try to explain all this, we would be an awful long time. We're going to have to treat that as a black box for now. The setup, though, is where the magic happens to tell the Arduino what you're doing. So, as I say, the pin modes are input. They don't need to be input pull up. In fact, they mustn't be input pull up because it won't go down to 0 properly. That's the switch. You don't have to use the switch, but I will, to set the correct temperature. So having turned the knob to 22, say, I'll then press it and go, that's it. And the code will then say, oh, you want me to go up to 22 degrees. Great. Here is where we tell the Arduino, or ESP32, which pin it is that you're attaching pin A and pin B to. So I've got pin A here, which is pin 32, and pin B, which is pin 4. These are arbitrary choices for me. Yeah, it can be any of the pins on ESP32. On the Arduino, can only be pin 2 and 3. And I've said, do it on a change, because we need to detect all stages, whether it's gone low, gone high, on each of the pins, right? So it's not just falling or rising, there's been a change on all of them. And they both run the same routine that we just saw. So the loop just says, if there was a movement, go and print out what it is, or go and find out first of all by checking it, was there one? And if it's not 0, which means it was a rubbish, it was a switch bounce basically, don't do anything. But if it wasn't a switch bounce, add in the right amount. Oh, and there's the push button, which I don't think I showed you, so let me just bring that back quickly. Right, so if I turn that now, there we are, so it's still going, and if I press the switch, bang, X 0 it says. Oh, and a 5 after it. I'm not going to explain that 5. That's for a future video. Not about rotary encoders either. No, I was playing about, and I've obviously left that in. Yes, okay. But this works very well. So Marko's done a great job, and his paper that explains all this, you can print off and read in the littlest room in the house if you want for many weeks until you understand it, which is basically what happened to me. But in between the house move and the rest of it, I couldn't really give it my full attention. But well done, Marko. That's really interesting, actually, and definitely a different way of doing it. In some ways, you could say, is it a better way of doing it? And I think it must be, because we're not waiting for 5 milliseconds or potentially longer if you've got poor switches on every single interrupt. Right, so we don't interrupt and then go, I'm not accepting any more interrupts for 5 milliseconds, even if there were no bounces and it was a proper interrupt. No, I'm not accepting it because it can't possibly be right. He's saying, I'll accept everything, but through the logic of his code, he can determine whether or not it's a valid transition of these switches from one state to another, the combination of the two, and says, yeah, that works. I got it wrong. It wasn't Banggood. It was in fact Amazon, but of course obviously a Chinese seller. The standard KY040 module, as they call them. And I bought 10 of these. Was it 10? No, pack of 5. Look, for £8.50, which I thought, that sounds a lot. How much is Banggood doing them for? And do you know what? With the VAT and custom stuff they now add on to all these Chinese warehouses, the advantage that they had in price is diminishing rapidly. Okay, here they are from Banggood. Now you can buy them individually, as it shows here, for £1.99, which I guess is a KY040, the same as what we just saw. There it is, exactly the same unit. They do them obviously in packs, so maybe looking at them individually isn't quite fair. Well, there's a pack here of 10 for £12.59. That's better value. Do you really need 10 though? Now we're talking about states of the switches that cannot possibly work. Yeah, you get combinations of the switches where it must have been a switch bounce to get that particular sequence of pulses, and you only get switch bounce with a rotary encoder like this with mechanical switches. You can buy optical rotary encoders. Why didn't I do that, you say?
Why didn't you do that then?
Yeah, exactly. And the reason is because they're really, really expensive. A Bourne's rotary encoder, which is a good brand, okay, Bourne's, B-O-U-R-N-S, rotary encoder is probably about £4. A rotary encoder costs like 30 quid, and it uses, I guess, infrared or LEDs or something inside it. You don't get any switch bounce whatsoever, and you can rev them up. You know, you could literally put them on a little motor or something. You can have thousands of revolutions a minute. But anyway, that's why I didn't use an optical rotary encoder. It just wasn't worth it. As I say, I'm still questioning whether I should be using a rotary encoder in my project for my heater controller, a thermostat control. Okay. Right, I'm not going to explain any more about this, because if you need to know how rotary encoders work, but the best thing is to watch now that video there that I did all those years ago, because at the time I thought, people aren't going to understand this, are they? What's happening? So I did it in quite some detail, and you watch that, you'll have no problems in understanding how the very simple rotary encoder works and can detect the rotational direction that it's going. Cool, I think we're going to leave it there. There'll be lots of links though down below for this. I'll link into Marko's code, his document that he wrote, his paper. I'll put a few links into where you can get these rotary encoders, whether it's Amazon or Banggood, but you can get them from just about anywhere. This model, as I say, is a KY040, but that just means it's connected up to the positive supply and ground and all that, so you don't have to worry about it in your actual code. Okay, I think that'll do for this week. Nice and quick and short, and I think if you get one of these and connect it up as I have done here, yes, I'm using an ESP32, but you can use an Arduino, I think you'll be pleasantly surprised. And once you've got it working, you think, ah, that's what I can use. I've thought of something now I can use this for. Yeah, okay. Right, that's it. So, comments down below, please. Suggestions on this and the multimeter. If you like the video, give it a thumbs up. What else was there? Oh, yes, if you want to subscribe, tick the notification bell as well as subscribing. Otherwise, you won't get told about new videos. And I think we are done, so I'll see you next time. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.